Please give a warm welcome to Dr. William Shirless.
Welcome to the technology discussion panel on software development and assurance. A quick word first about AI. So most of you know that DARPA has been staging programs to advance AI for more than half a century. Dr. Tompkins referred to this yesterday. And almost a decade ago, as everybody knows, AI, or specifically machine learning, crossed a threshold. And it's now in everybody's toolkit. Before that, it was esoteric and special. Besides being in the popular imagination, it is in the imagination of those who are conceptualizing the future mission, and good things are happening. But it's been a bumpy road to get here. Many successes, and also some crises of expectations. And in fact, Dr. Tompkins showed a chart yesterday that showed the waves of AI, but also the waves of investment and disillusionment along the way. So we're going to talk today about the engineering of highly assured software systems. And I tell the AI story because I believe that we're in a similar state to where we were with AI a decade or so ago. We have a long DARPA history, many successes along the way, but also some crises of expectations. It's been a long game. Our premise today is that the long game is starting to pay off. There's work to be done, but we're nearing a threshold. We're at a point of timeliness in developing the technology for large-scale, highly assured software development. So the practice that we're talking about combines four elements. Very high assurance, because we have highly capable adversaries, cyber adversaries. Continuous evolution, because we want to be responsive to adversaries that are nimble to shifting threats of all kinds, but also to the emergence of new capabilities, including AI and sensors and enclaves and the like, and also to our own more rapidly evolving concepts of operations. A third element is continuous test and evaluation, so we can deliver these to the mission in an ongoing fashion. Some people say continuous ATO, authority to operate. And a fourth element, becoming more important now, is high levels of resilience, which is the ability to operate through attacks. When everything is interconnected, we cannot allow an attack to cause a total system failure. So we have to somehow operate through. And the scale of interconnection and also the attack surfaces exposed is increasing. So all of these are necessary for today's mission concepts, and there's real benefit from coupling these four elements together. And I'll also say that these are aligned with the Defense Digital Engineering Strategy, which talks about these elements as well. So we're going to talk today in the panel about some examples of what's possible now, including examples, some interesting examples from commercial practice at Amazon and Microsoft. And then some enabling computing technology advances that combine deep math, good tool engineering, and better definitions, better practices. And then finally, what more we need to do to cross the chasm for mission systems, how we can better integrate these ideas into our acquisition ecosystem. So we're talking about software today, and you know that software is strange and special stuff. And it's not just because the aerospace engineers love how much it weighs, right? It's also because there are really no hard bounds on how far we can go with software. Mark Rosker was speaking of quantum computing and the laws of physics. Well, with software, we have no laws of physics to constrain us, no asymptotes. And in fact, this is why last year the Deputy Secretary of Defense said, the ability to securely and rapidly deliver resilient software capability is a competitive advantage. Software capability is a competitive advantage that will define future conflicts. So software is in nearly all of our systems. And we could argue, in fact, that it's perhaps the most critical building material of our age. And our adversaries know this. This makes for an ongoing Red Queen competition. Now, when we speak of assurance practice, let's look at the baseline. It's not where it needs to be. In many engineering projects, we have a culture of compliance, adherence to process, measures on process, hoping that this will result in product quality. Why is this? Because it's too hard to measure the product directly. At DARPA, we focus on metrics. Metrics on software are really challenging to create. Now, process measures work really well for repetitive manufacturing. They narrow the bell curve, they enhance predictability, minimize variance. But for creative engineering, which is what software is all about, it does help a bit, but it does not help us go the distance. The executive order on cybersecurity that came out about almost 2 years ago included some elements that are focused on direct evaluation of artifacts, software bill of materials, zero trust. And so this panel is about the benefits of going further in this direction of direct evidence, the many kinds of models and analyses directly tied with execution artifacts. Now, we've had some great successes in this area. Formal methods, mathematically based approaches are now routinely used for certain very special categories of systems, including, for example, commercial flight controls. The question is, how do we scale this up to larger and more complex systems? How do we make these techniques more usable by developers and evaluators? And also to a broader range of kinds of software projects, sensors, cyber-physical, real-time, machine learning, AI engineering, right? How to integrate this with our baseline engineering practices and acquisition practices, and also how to make it all affordable. So the value proposition is more compelling than what we're doing now with integration, and as compelling as it is in the commercial world. So I want to mention 4 positive touch points, and then I'm going to mention 4 challenges, and then we'll open it up for the panel. So the first positive touch point is a program at DARPA that concluded about 4 or 5 years ago called HACMS. Okay, a quadcopter control system was verified, and it was proved to be correct. That was the verification. Well, some years later, the program manager who succeeded the original program manager for that project came to me and said, I was office director at the time, came to me and said, let's put this out at DEF CON to all the hackers and see what they can do with it. And I felt this was pretty risky, but we have to try it. We did. Nobody hacked it. 4 years after it was completed. The hackers were 4 years smarter, and the system was still what it was 4 years earlier. But more importantly than that, the verification approach in the engineering of that was highly selective. The SEL4 operating system, certain key architectural choices allowed the entire quadcopter to be achieve a level of trustworthiness, but the verification effort to be focused very narrowly. Second is we have really good established use cases in the tech sector, most notably at Microsoft, Google, Facebook, and Amazon. We're going to hear about some of those shortly. And there are business cases behind these adoptions. Third, we have now sneaky ways to incorporate these mathematical approaches into the engineering of systems, into the mainstream of software development. We call this hide the math, or invisible formal methods. And there are a lot of examples of that, including, for example, TypeScript, which runs in all of your web browsers, has displaced JavaScript, untrustworthy JavaScript, with a trustworthy tool that helps developers be more productive. And so these hide the math approaches enhance productivity, right? And so they look a lot like what is being displaced. And by the way, the software becomes more secure. So a fourth example is languages designed for specialized applications, domain-specific languages. A good example is Cryptol, which was built for cryptographic applications, is now mission critical at NSA. Okay, all good. But now here are 4 points of challenge. First, our mission systems, unlike the systems at the companies that I mentioned, are integrated from diverse elements from diverse sources with rich supply chains, working across business boundaries, arm's length relationships. So there are challenges of transparency and there are challenges of incentives. Second, well, to be blunt, the sizzle and glamour of AI, which I mentioned at the beginning, does not really exist for systems engineering. A former DARPA director told me, you know what, Bill? These engineering and software programs sound pretty boring, but they're super important for the mission. You know, the software on the airplane, it's not as pretty or as imposing as the airframe, but when you talk to Air Force guys about airplanes, they talk only about software, at least in my experience. Third, the adversary is super engaged and throughout the supply chain. That includes open source. And then fourth, with respect to the computing hardware, with Dennard's law failing, clock speeds leveling off, the hardware folks are introducing all kinds of new optimizations which create new attack surfaces. So we're here to talk about ways ahead, how we can expand the envelope on verification and other advanced methods for the most critical systems. Includes scale, affordability, integration into process. There's an argument that improvements of this kind are a key enabler for systems that can continually evolve with continuous test and evaluation. The test and evaluation community is now very much engaged in this. They talk about moving to the left on the timeline and making use of direct evidence, models and analyses and the like to support this continuous evolution of systems. So this is why we put these pieces together. So now let me introduce the panel. And our panelists have really great experiences to share. So first is Jeanette Wing, who I've known for 40 years. I have to say that, including many years at Carnegie Mellon. She's a great leader in formal methods and in the computer science community. She was an assistant director at the National Science Foundation, responsible for computing technologies. She was also a senior executive at Microsoft, and she's now executive VP of research at Columbia. And she's known for her research in formal methods and software assurance, and for promoting the idea of computational thinking, and most recently, a book on data science. So, Jeanette. And then second is Natarajan Shankar, who I've known only about 30 years. He's been at SRI since 1989. He's a distinguished senior scientist, SRI fellow, and he received a really major award for work on theorem proving and formal verification, the 2022 Herbrand Award. He's a major pioneer in formal methods. He's advanced both the mathematics and the tooling, and he's proven the benefit through a range of significant applications. And then we have Mike Hicks, who I've also known for a long time. He's a senior principal applied science at Amazon Web Services. He's helping make the cloud more trustworthy. His previous 20 years were as a professor at University of Maryland, focused on programming languages and software security. And he's known for work on the very recently announced Amazon Verified Permission Service, and his work previously has been applying programming language-based ideas to software security. So each of the panelists will now offer a short remark, and then we'll take some questions. I'll start with a few, and then we'll open up questions to the attendees. Let's start, please, with Jeanette.
Thank you, Bill, and thank you, DARPA, for inviting me to this DARPA Forward conference. I am a bit of a DARPA brat, having gotten DARPA funding when I was a young faculty member at Carnegie Mellon with Bill. And then later I served as a member and the chair of ISAT, which is an advisory committee to I2O. What I'm going to talk about is a DARPA hard problem. In fact, it might be insurmountably hard. And I call it trustworthy AI. So first, let me motivate why I want to talk to you about trustworthy AI. And Bill hinted at this already. AI systems have already exceeded the ability of humans to perform certain tasks. Object recognition, speech recognition, play and go. The promise of AI is phenomenal. They're going to drive our cars. They're driving our cars already. They're going to help doctors diagnose disease. They're going to predict when the Arctic sheet will melt. They're going to predict 45 days in advance when the medical supplies need to be shipped over the Pacific. The promise of AI is huge. The implications are huge. However, we also know that these systems are brittle and not fair. And for many of the systems that Bill was talking about that, in fact, disrupted us 10 years ago, I'm speaking specifically about deep neural networks, we don't even know how they work. We can't explain the outcomes that these systems produce. So why should we trust them at all? There's no reason to trust these AI machine learn-based systems. And they are going to be making safety-critical and life-critical decisions for all of us, for the warfighter in the battlefield, for the doctor who's doing that triage. So why should we trust those systems? No good reason, actually. So the DARPA hard problem is how can we assure trust in these AI systems? And there are two ways in which perhaps this is an insurmountably hard problem. Because for decades, as Bill mentioned, we have been working on trustworthy computing, making software and hardware systems trustworthy. In fact, at the turn of the century, the late 90s, early 2000s, there was a huge push by academia, industry, and government to focus attention in research on trustworthy computing. Bill Gates wrote that very famous 2001 memo on trustworthy computing for Microsoft. The National Science Foundation started many programs on trustworthy computing, followed by a National Academies report. And of course, DARPA has funded trusted computing for many years, and the academic community has responded accordingly. And some of the programs that are funded by DARPA and NSF are continuing to be funded. So that's trustworthy computing, which is already a DARPA hard problem. Now, I'm going to up the ante in two ways to explain why trustworthy AI is even harder. First of all, what do we mean by trustworthiness? For computing systems that we know and love, we usually mean reliability, security, privacy, usability, availability. We actually know how to quantify those properties and determine whether a computing system satisfies one of those correctness properties at all. And we have expertise behind me who have built tools and languages and deployed tools and languages to actually verify whether a computing system is trustworthy with respect to those properties. And we continue to plug away and make continued success. But for AI, we're talking about not just those trustworthiness properties. We're also upping the ante and talking about robustness and fairness and explainability and even ethical issues of AI systems. And we never had to talk about those kinds of trustworthiness properties before. So I challenge my colleagues in formal methods and programming languages. What would it mean to verify an AI system with respect to those kinds of properties? So that's one way in which trustworthy AI ups the ante on trustworthy computing. The properties are different, but they're important. The second way is the inherent probabilistic nature of a machine learned model, which would probably be in any AI system today. In computer science, we're pretty much satisfied reasoning about digital systems, Boolean logic, true or false, on or off, yes or no. But for AI systems, especially deep neural networks, they're inherently probabilistic. There are probabilities floating along those edges in a DNN. There are probabilities produced as an outcome of those machine learned models. And the properties that we care about are often expressed in terms of probabilities or stochastic processes or data distributions. So now we can't just reason using straightforward Boolean logic and temporal logics that we've been using for decades to reason about concurrent and distributed systems. We probably need to use probabilistic logics and hybrid automata and all sorts of combined mathematics. And that's something that computer scientists tend to shy away from. The last thing is the model is inherently probabilistic. The properties themselves may use probabilities, and the logical frameworks in which we have to verify these systems may very well have to draw on new kinds of mathematics, new kinds of reasoning tools, new kinds of logics, and all of that has to scale up. So, is this not yet a hard enough problem for you? I hope it's hard. I hope I've said that it's hard enough, it's compelling enough. So, what I have been promoting for the last year is a new research agenda, which I call Trustworthy AI. And it really is a call to arms for 3 communities to come together: the AI community, the cybersecurity community, and the formal methods and programming languages community. And it really is a challenge to the formal methods and programming languages community to say, let's look at these new kinds of systems. And these new kinds of systems are not systems that human beings write. These new kinds of systems are systems machines write. So, Trustworthy AI. Thank you very much.
Thank you, Jeanette. Shankar.
Thank you, Bill and Jeanette, for setting the agenda and the tone so beautifully. Before I get to my remarks, I'd like to take a moment to remember my dear friend and former colleague, Drew Dean, who passed away unexpectedly last August. So Drew served as a DARPA program manager and actually led several highly impactful programs. He grew up in the San Diego area, and he's dearly missed. Now for the software development and assurance pipeline. The first point I'd like to make is software is truly amazing, and it's eating the world for a good reason. We use it to operate everything from kids' toys to self-driving cars. With this ubiquity of software, particularly bad software, comes a huge cost. Bugs in software are costing us a pretty penny. The estimated engineering cost of bugs is annual estimated cost is supposed to be around $2 trillion. Cybercrime alone annually costs us about $6 trillion. And that's trillion with a T, and these are possibly underestimates. So the cost is actually huge. The other thing about software is that it's hard. Software can be about lots of different things. We expect it to work in so many different application domains. We expect it to work in medical, financial, cyber-physical, AI. There's so many domains, and we can't, as software developers, be experts in all of these domains. It's expected to work in a number of contexts. Yesterday, you heard about software working or not working in the Arctic. It's expected to work across a number of different platforms. And so, software development is inherently hard. On top of this, we're operating with a software stack. even though I regard the modern software stack as one of humankind's greatest engineering achievements, it's rife with what I call original sins, that things that design decisions that were introduced in innocent times, but in the modern world, you can't get away with some of these choices because software is probed and attacked relentlessly. The bugs in software can be reproduced and exploited at scale. Testing is quite an expensive way to carry out software assurance. It actually offers very meager assurance at enormous cost. So, we need to think of other ways of making sure that our software works. So software needs assurance. So software, needs to move away from this idea that you're going to have rough consensus and running code to something that is a kind of scientific mode of assuring that, the software that's been delivered will actually work without actually having to test it after the fact. So the cost of actually fixing bugs late in the design lifecycle has been estimated to be around 100 times that of fixing it early in the design lifecycle. And many bugs in software actually get introduced early in the software design lifecycle. So the form of the assurance has to be, in some ways, include strong claims supported by reasoned argument backed by verifiable and reproducible evidence. So typically, in a software assurance argument, you would have a way of analyzing the requirements and making sure that these requirements are actually sensible and consistent and actually capture the intended behavior of the software. You would have ways of actually making reasoned arguments for why the design actually does meet those requirements. And as Jeanette mentioned, some of these requirements, they span a significant spectrum of ilities. You expect the software to be performant, functional, resilient, persistent, robust. So these are all things you cannot achieve through testing alone. You need to have a process for actually creating assurance arguments that can validate the software. Now, one thing about software that's interesting, compared to many physical engineered artifacts, is that it's a mathematical artifact. We can actually get software 100% correct, modulo messy physical reality, modulo the genuine difficulty of writing correct specifications. So, these are big modulos, but, it is in principle possible because software can be actually viewed as a formula. You don't have to test it concretely. You can actually analyze it abstractly and make sure that it doesn't, for example, crash or deadlock or leak or corrupt information on all inputs, on all possible inputs. And that's what we do in formal methods, and we treat software as a formula. We build tools that can analyze these formulas on all possible inputs and ensure both the presence of, we can actually demonstrate the presence of bugs as well as their absence. And so some of these tools include static analyzers, model checkers, theorem provers, code generators, runtime monitoring. There's a whole suite of tools that can be brought to bear. And the challenge, of course, is to make sure that these tools can scale up to the size of software that we're dealing with. So if we have all this, are we done? Is it the case that you just take your software, run it through a static analyzer, and it tells you, yes, the software is good? That's not at all the case. The scalability will always be a problem for us. And the real bottleneck is not these tools. These tools actually can be used both economically and feasibly to analyze complex software, mostly by experts. The problem is that we have a design bottleneck. Software design is hard. And if you want to design software for assurance, you have to focus on something that I call an efficient argument. An efficient argument is one where any flaws in the design are actually amplified in the argument, and any flaws in the argument are actually amplified in the way in which the argument is structured. In particular, that means that you're using certain languages, architectures, and tools that a skeptic could actually identify any flaws in it with a fairly low amortized cost. And so these are the kinds of things that we're doing to actually make sure that formal methods can be part of an efficient argument-based design. We are looking at formal architectures. Bill mentioned the HACMS project. In that, we developed an architecture framework called Radler, where a number of guarantees on the real-time behavior, on even many of the security guarantees are provided at an architectural level. And these guarantees are reusable across many different projects which use the same architectural framework. We've introduced the notion of ONTIC types, and actually we're analyzing many software systems with these ONTIC types. So normal programming language data types look for things like whether it's an array or a struct, but ONTIC types actually look at what the data value actually represents. Is this integer something that represents ground speed in nautical miles per hour, or airspeed in meters per second? Is it something that is perhaps a user ID, an IP address? So all of these distinctions actually are captured by ONTIC types. And then you can look at the proper use of these data values. You can look at, for example, whether private information is being leaked and so on. So that's something that we do with ONTIC typing. And so this can then be composed into a assurance argument in which you actually exploit abstraction as a way of achieving scale. So my final point is this, that we need to move away from the kind of traditional software practices to one that delivers explicit assurance in the form of something that I call a software proof of virtues. Just having an SBOM is not enough. You need to have a software proof of virtues, and this has to be the coin of the realm. This is what you exchange with others. These are things that you compose into larger software proofs of virtue, and that's how we actually are able to get some handle on both the cost and the risk of software. Thank you.
Thank you, Shankar. Mike.
So I'm going to go back 2,500 years to Pythagoras, who proved the Pythagorean theorem. Maybe you also proved it in your high school math class, that the sum of the squares of the short edges of a right triangle equal the square of the hypotenuse. And then you did a proof where you reasoned one step after another, taking facts that you knew, until finally you had the result, QED. That's mathematical reasoning. For the last 100 years, mathematicians and computer scientists have tried to mechanize mathematical reasoning, create formal logic, create the rules of what reasoning means. And for the last 50, computer scientists have tried to automate logical reasoning. And we have scaled it all the way to the point that we can achieve the things that were just discussed, being able to prove properties about air traffic, collision avoidance systems, or medical devices, or as it turns out in the case of my employer, the cloud. For 20 years, I worked at the University of Maryland as a professor doing research on technologies, and now I have the pleasure of working at Amazon, where we're putting these technologies to actual use. It's quite astounding to see 150 scientists working at a big company where the company is making a big bet on these technologies actually working and providing value to their customers. So I have listed here on the slide just a handful of some of the services that Amazon uses that have formal reasoning, automated reasoning as part of their core. So the first one, I Am Authorizer at the top. This is the authorization engine that governs whether or not you're able to access a particular AWS resource. If you have a simple storage service, S3 bucket, and somebody goes to access it, well, are they allowed to access it or not? There's a bunch of policies there. Well, it turns out that those policies are queried 43 trillion times per day. That's 500 million times per second. So it's really important that this authorizer is correct. And now there's an effort underway to use formal methods, use that automated reasoning to establish that it is. Now, the authorizer has been working just fine for the last decade. Why do we want to make the switch now? Well, it turns out that automated reasoning gives you agility that you didn't have before. Once something becomes so important, it's used 43 trillion times per day, it becomes very difficult to feel safe when you change it. It might be that some small change you made has an unintended consequence. If I have a proof, if I'm able to use automated reasoning like Pythagoras did, that the changes I make still satisfy the specification, I can feel a lot more confident that the change I made is what I intended, and I can quickly deploy it and satisfy my customers. We've also used some of the other technologies mentioned, static analysis, model checking, for example, to prove safety properties of the FreeRTOS operating system. This is a very popular operating system used in Internet of Things devices which connect to the cloud. Using off-the-shelf tools, but then adapting them to work for our use cases has been very satisfying for our customers. The first 5 elements on the list there are basically using high assurance development methodologies, but the last 2 are about providing automated reasoning to customers themselves. So CodeGuru is a service for static analysis that customers can use to analyze their own code bases. I can have my Python or JavaScript or Java code base. I can point CodeGuru at it, and it will do an analysis looking for potential security vulnerabilities and flaws. One thing that's great about that is that every time you make a change to your code repository, CodeGuru will rerun and notice any new flaws that might have occurred. So it's part of what I show on that last column there, the continuous assurance pipeline. We want to make sure not just that you've proved that your algorithm works once and then you forget about it and move on and do something else, but that it's continuously reproved every time that we make changes. And this is true within our own services at Amazon, all those things that I just spoke about, but it's also true of those services we provide to our customers. So the one last example I want to mention is Access Analyzer, which is at the bottom. So remember those AWS policies I mentioned that the authorizer is enforcing. Well, how do you know when you wrote all your policies that you did it correctly? You maybe intended that no public unauthenticated user can access a particular set of buckets. But it might be that the combination of hundreds of policies you wrote conspire to inadvertently allow public access. So Access Analyzer is an automated reasoning system that analyzes your policies and is able to, in a sound way, that is without mistakes, warn you if you're violating this invariant that you had in mind. So that's the detective portion on the right column there. You can take it one step further and actually block any policy that you try to add that would inadvertently allow public access or even suggest a correction. So putting all of these things together, having high assurance methodologies that we still need research and development to advance, and the continuous assurance pipeline can raise the bar on providing reliable and agile services for our customers. And so I foresee Amazon and other tech companies as well investing them well into the future.
Great. Thank you, Mike. So I'm going to pose one question to the panel, very lightning round question, and then we're going to take questions that are posed from the audience. And just to echo Mike's really critical point that our ability to model and reason about systems directly is an enabler of agility, and agility is essential now in the modern mission. And one of the reasons why this is a timely topic is the acquisition community, the contracting officers, the program offices, the PEOs, the acquisition executives, all recognize this new reality and the essential need to be able to build systems that can continually evolve. So one of the challenges in our mission systems is there are many, many attributes, what Jeanette called the ilities, that are significant to coming to confident judgments of mission worthiness. And so I want to ask, I'll start just Shankar, a quick response on what are the next set of hard attributes of systems that we could need to develop models for that we can reason about. There are a number of attributes that we can reason about now. What are the next set of challenges that we need to take on?
So with software, it's really all of the above. You need to, essentially make it watertight because an adversary can drive a truck through any single vulnerability. But in terms of the attributes that you would like to have software hold, there are certain things that are generic and there are certain things that are specific to what the software is meant to do. The absence of runtime errors is certainly critical. In particular, memory safety, I think, is absolutely paramount. And that would be something which, if you can get that, because it's such a generic property, you can actually make sure that a lot of annoying things that to do with software can be eliminated. But from there, you want to move on to things like cyber-physical systems and actually look at cyber-physical behavior. You want to be looking at financial systems to make sure that financial systems are secure. Right. And so you want to go into more domain-specific attributes.
Well, it's interesting for memory safety because the way that's being addressed is through a combination of hardware-level interventions, software programming language and runtime systems, and then also high-level reasoning. We really need all of those to get to a confident judgment. That's right. Do you want to comment on this? Can you tell us what are the next kinds of properties that might be of interest at AWS?
So I think that to be honest, I would say not the properties, but the way to specify the properties, I think is of greatest interest. That right now, automated reasoning technology is limited to a series of experts who are really good at math and know how to write those specifications down of what they want their systems to do. And if you really want to democratize this technology, you need to have, in some sense, low spec, just like low code, or no spec, no code environments where anybody can take advantage of these systems. And the Access Analyzer system that I briefly touched on is one example of that. We're doing 2 billion SMT queries per day in using Access Analyzer to allow arbitrary customers to take advantage of this technology. So I would say that's really, to me, the big challenge is how do you make saying what you mean as simple as possible and yet still rigorous?
Thank you. So Mark Rosker gave a really engaging presentation on quantum. And so we have a question on quantum that relates to Jeanette's comment about the probabilistic, the stochastic nature of machine learning nets. And the question is, can quantum computers be used to verify probabilistic AI systems?
I want to answer your first question, Bill. You didn't ask me, and I actually was part of my spiel was to talk about these new kinds of properties that we have to worry about for AI systems, like robustness and fairness and explainability and so on. Robustness, I do believe we can have a handle on formalizing and then shipping it off to the mathematics world and just churning it out. Fairness is much more difficult. I'm not sure how much fairness is important to the DARPA community, but it is definitely important to the tech industry. And in fact, I think the fairness of some of the AI models are under attack, if you will. The unfairness is being highlighted. And these automated decision systems are being used to make judgments about people. They are used to determine, government agencies are determining who gets the milk money, whose garbage gets picked up first, who gets low-income housing based on these automated decision systems that are fed historical data. So one thing I didn't mention is, I think another difference between traditional formal methods and trustworthy computing and trusted software and trustworthy AI is the role of data in the equation of does M satisfy P? Does a model satisfy a property P? I think that because data is so important in driving the training of this model, we can actually think of that data as another artifact in the expression of determining whether a machine learned model or an AI system satisfy a property. And so we shouldn't ignore the data that we're using to test and train the AI system. Now, you asked about quantum computers. I know a lot less about quantum computers, but they seem, I think maybe the answer is yes. Why not try? I mean, we don't even have a quantum computer that can actually do anything sophisticated yet, but we can definitely explore how it could be used for verifying AI systems.
You want to take this? So we have a question about GPT, larger natural language processing models, such as GPT, to play a role in fixing and optimizing real-world computer source code. So there's actually an enormous amount of work going on in using various kinds of AI and data-intensive techniques to mine the enormous base, hundreds of billions of lines of code that are out in the world, open source and otherwise, as sort of a way to mine that code base for ideas and solutions to make repairs. In fact, there's a technology of automated bug repair that's been around for a long time that follows that model. What are your comments on the use of these larger AI systems for this purpose?
Yeah. By the way, great question. You've seen these new models actually generate code. They're able to digest large repositories from GitHub. And what this actually points out is that so much of what we do actually has such low entropy.
Yeah.
That, but there's a risk in that. The critical things that we do, the things that we do that are actually very creative, actually do have high entropy.
Right.
So
Nature of creativity.
there is a risk involved in this. But indeed, I think for the most part, for at least naive users, having the support of something that is able to actually mine the existing data and make statistical predictions, statistical corrections is actually hugely valuable.
Maybe we can mine both programs and proofs.
Yeah. And the other part of this is also the natural language. That's another thing, which is that there's a lot of information in the world that actually is redundant. I mean, so you can use it to check on everything else. And in one project, actually Ops 5G, we are taking the 5G specifications in natural language and actually building reference implementations directly from it. Actually, Tejas Patel, the program manager, is here in the audience. And so there we are actually working straight off the documents. And it's a two-way street. You need to write better documents as well as be able to have AI do this.
Well, that concludes our session. Thank you very much, panelists.
Thank you, Bill.